It damps the annual cycle of temperature in the tropics, in particular. In the winter, the oceans release heat they gain in the summer. The weather on the west coast of continents is warmer than the east coasts, etc., etc. The ocean transports polar, and that makes the planet, on average, than it would be otherwise. If there were no heat transport, sea ice would go toward the equator. As we found when we did a no heat transport experiment, I didn't put a slide from that. On long time scales, the ocean is, of course, a big heat sink, if you will, in the context of the anthropogenic global warming problem. A lot of people are trying to figure out how much heat is going into the ocean and should go. Likewise for CO2, as the ocean also has a life of its own. It's not just a heat sink. It actually can generate variability. Yes?
I'm embarrassed I don't know this, but what is the percentage compared to the atmosphere of heat transport poleward?
Depends on the latitude. The ocean heat transport peaks at a lower latitude than the atmosphere, and maybe at 15 degrees north or something like that. It actually is larger than the atmosphere's transport at those low latitudes. In the extratropics, the atmosphere dominates.
Sorry?
In the extratropics, the atmosphere dominates.
Thanks.
Well, one of the big latitudes where like temperatures considerably lower. Right?
Yeah, it dominates. But there are specific regions in the world where this ocean heat transport, as small as it is compared to the atmosphere, is fairly important. So if we want to try to model these effects, we need to understand what determines the scale of the model that we try to build. And so I will always distinguish between the things that are kind of internal to the ocean model versus forcings in the ocean model. So since this is kind of a casserole of a talk, I'm try to make an outline just to remind everyone where we are in our progress. So this is the outline, and this is some terminology. I'll frequently use spare trip units, which is a kind of arbitrary thing named for a famous oceanographer. It's more convenient than writing 10 to the 6 cubic meters per second. A coupled simulation means that you have an atmosphere model running over an ocean model, and the two see one another's states. A standalone ocean simulation is one in which we prescribe the atmospheric state, and so the atmospheric state is independent of the ocean state. Obviously, that's not always such a good thing, as you will see in a couple of cases. Mesoscale.
Max,
Yeah.
state means CO2, temperature, radiation, what kinds of stuff?
Anything you want in this
Sure, what's the status right now?
model?
No, in your talk, I guess. I mean, the standalone ocean right now, what input does it need for, what boundary conditions does it need at the surface?
Oh, well, everything you need to calculate heat fluxes and freshwater fluxes. And if you want to have tracers in the ocean, you want to have information to those fluxes as well. And wind stresses.
Even stretch.
Precipitation?
Yeah, freshwater flux. So the term mesoscale in this context means something smaller than, it's a smaller length scale than in the atmosphere. In the ocean, it means something on the order of tens of kilometers. GM is just a shorthand notation for this formulation.
muscle model.
This isn't our standard ocean model, this is one that's higher? It's not 1 by 1.25, it's 1 by 1?
Oh, yeah, it's actually 1 by 1.
Oh, okay.
And so it has a pretty standard formulation of the form of mesostable tests, but there are various parameterizations giving you like the vigor of the eddies at any given location in the ocean. The diaphysical mixings is a standard scheme. There are other options currently available. The atmosphere that used for these experiments include standard Air 5 atmosphere at the standard 2-degree resolution. There are also a couple of results from double resolution version on the cube sphere grid, and these are the two acronyms for the prescribed atmospheric state.
So the grids don't match up.
When we're running
The ocean to the there's not nice.
there's
nice.
regridding happening, but
It's too bad.
I think it will always be the case that people will want to run the ocean at a finer resolution than the atmosphere.
Well, if it were integral, you wouldn't run into problems.
Well, for this case, it is actually just a subdivision of the
Oh,
atmosphere.
oh.
And so the first role of the ocean, which I actually won't talk very much about, is the relation of the seasonal cycle. I just want to point out that the ocean is on average almost about 4 kilometers deep. But the part of the ocean which participates in the annual cycle is only a few tens of meters deep. So the so-called mixed layer, where the mixing is driven by mechanical motion of the winds and in the winter high latitudes, the heat losses can destabilize. We want to make an ocean model that is doing a good job. The next layer, obviously, is sufficient vertical resolution, and so you would want at least maybe 10 grid points within this 100-meter range, which is, and we don't not quite there yet in the resolution department. But we will increasing the vertical resolution is cheaper than increasing the horizontal resolution.
I have a question. Why does the mixed layer vary so dramatically, especially around Antarctica?
Because around Antarctica, at the high latitudes, this winter heat loss stabilizes the water column. So it creates fluid which is denser near the surface than below. That causes an overturn gravitationally unstable.
But it looks like like in the Arctic, it looks like the mixed layer is very shallow.
Yeah, I messed up this missing. There are 2 types of missing values in the file. I didn't properly mark those as missing.
Oh, I see.
So these are the 2 things driving the mixed layer dynamics. So that's the net heat gain averaged over a few years. So the ocean is gaining energy in the deep tropics. It's transporting some of it to the subtropics, and in the western boundary currents, the rest is transported to the high latitudes. And I just wanted to point out that 2 things. First, welcome here to
travels.
Observations?
This is actually the diagnostics from the standard
Okay.
ocean, so they are as close to observations as.
So is the equator, since it's right on the equator, does that mean that's sunlight as opposed to ITCZ?
This part?
Yeah.
Well, this is the upwelling of the very cold water. So the net heat flux is the balance between the solar radiation and the sensible latent heat fluxes. And because this cold water upwells, it loses less heat to the atmosphere, or it actually gains. You have to look at the sensible heat fluxes. So it's just the lack of this cancellation between the solar and the.
I didn't realize there was an upwelling at the equator.
What?
That's why the fishing is so good there.
Yeah.
Didn't know. I don't know anything about the ocean.
Max, but you say that in the buoyancy gain, you also have the forcing of the salt restoration, right?
Yeah, but in the standalone ocean context, that's kind of like correcting the precipitation.
But I mean, it does have regional signatures.
It seems really interesting to me that the locations of your Maxwell surface fluxes are hardly coincidence with your deepest mixed layer depths.
Well, this is the annual average. So that will show the whole winter, or show the maximum over the year. It would give a different picture. I was just trying to illustrate that it's only the upper part of the ocean which participates in on short time scales in the climate. So the next ocean rule is heat transport and microscopic composition. So I'm going to slightly change the subject from this is terrible.
Yeah.
Tell it to not go to sleep or something.
Oh, that's yeah.
No, isn't
This
it
happens
this up
every
here?
this happens every time.
Because this is not centered on that screen, obviously.
It was, but it went to sleep.
So he has
Yeah, it happens every time.
So he takes it and zooms in, and then zoom in, and just kind of slightly moves left or right.
Okay. So I'm
Still not centered.
Excellent.
So the ocean heat transport rule I'm going to change into temperature and circulation, because those are the diagnostics I'll be plotting. Could have shown heat transports themselves, but temperature, for example, is a bit better observed than the actual heat transports. And heat transport is a product of temperature and circulation strength. So I'll be looking at the ocean model skill as in the context of temperature biases. Temperature drifts is another term for bias. And circulation strengths, how close do they stay to initial values? Do they run away to large values, or do they collapse to zero? We'll see examples of that. Okay, so the circulation is determining the mean state of the ocean, or this is the SST pattern. All know the tropics are warmer than high latitudes. I'll just point out that the western parts of the basins tend to be warmer than the eastern parts. You see the upwelling signatures. Different shades of red, unfortunately, doesn't look very well. So these are the surface currents in the ocean. Western boundary currents flow poleward. We have a very strong circumpolar currents at high latitudes in the southern hemisphere. We have the North Atlantic drift, which is the upper limb of the so-called conveyor belt. And so the second circulation that's important to consider is so-called thermohaline circulation. Thermo means
it a contouring problem? I don't see the cold tongue on the equator. I mean, two slides back, I had the same impression.
Yeah, the shades of red,
Yeah.
unfortunately, there are two shades of red, and you know, this color scale goes 0 to 30, and you could have chosen one to highlight the cold tongue where the upwelling is happening.
Yeah, the mixed layer is much more diffuse in this model than what the observation shows.
This is observations.
Then you, and that was the other plot, the potential density plot.
Observations also.
But without a cold surface, I'm amazed that you get that much heat flux into the ocean at the equator. Like one of your earlier slides showed this big heat flux.
This is the observed temperature, and it's just a contouring problem, as you said.
Oh,
You don't see
okay.
the cold tongue there. The shades of red are not showing up.
So in the model, can coastal waters be treated the same way as just open ocean, or is that something separate?
Yeah, we don't. It's pretty hard to represent coastal dynamics, everything that's going on. At this horizontal resolution, no one really tries too hard, I guess.
But so the ocean is really a clear boundary then in the model. It's like ocean or land.
So this is the schematic of the so-called conveyor belt, whose existence was inferred in many ways, but one of them being the radiocarbon age of ocean water. It was noted that the radiocarbon age of water in the deep Pacific was hundreds or even more than 1,000 years. And as more data has been collected, people have been able to examine this notion of the conveyor belt more in detail. And so this is showing the Pacific age as a function of depth, latitude, north being on the right. So the oldest waters are over 1,000 years old, which is where deep water has finally come to the surface. And this diagram is slightly misleading in the sense that the role of small-scale mixing is actually quite important in allowing the cold water to rise to the surface. If there were no mixing, cold, dense water would just stay down there. And lastly, mesoscale eddies are a very important component of ocean circulation.
So this age of carbon is essentially the assumption there's like no biological activity going on in the deep ocean. And so that age tells us like how long the water has been deep. Is that it?
Yeah, essentially how long it's been away from the surface.
Is there any biological activity down there? Or is this
Well, I guess there are some nice pictures of strange fish, giant teeth.
There's bacteria.
Giant
It
squids.
exists.
They're just playing with whatever isotopes they're swimming in.
Maybe you could look at it like oxygen or something now, more to get a better idea where the stuff is living or where stuff's not living.
So, people like to look at
maybe they're just not enough. You know, there's no plankton, no photosynthesis.
No.
so people like to look at satellite images of that was a good idea. Like to look at satellite images of clouds, and you can also do the same thing for ocean color and generate false color images which show how ocean eddies are mixing and swirling the water actually want a numerical model were to resolve those, the resolution would have to be maybe 5 kilometers or so. To resolve a feature, you want at least 8 grid points or something like that.
This is not true color. This is something to
False color.
pop that out.
So people have, as computers have gotten more powerful, people are starting to try to run global eddy resolving, eddy permitting simulations. So this is one image created down at Goddard, and it's kind of a new good. We haven't even gotten to my research yet, but just to give you a sense of lesser scale appearances. You can see that they're pretty ubiquitous, and so we're not just missing out on some Gulf Stream groups or anything like that. They're everywhere, and they're everywhere acting. They're everywhere as kind of a manifestation of what is called baroclinic instability in the atmosphere, the horizontal gradients of density in the ocean.
What's the time scale, Max?
No, this is
Top right, you can see it.
That would be some good
It moves.
observations. I don't know why they're showing us satellites flying around.
Yeah, this has all the trimmings. It has outer,
Looks like a Van Gogh.
Got it.
This is a group down at Goddard.
Clearly they have too much money.
Suggestion with the
I think it's very Van Gogh.
I was thinking the same thing. It was a programming Van Gogh.
When you get to the open ocean here, that makes it feel like a lot of it is coastlines. Except for, it is involved in the formation of the main eddies.
So what's their resolution next?
Strong currents. It's usually at the edges of strong currents.
So did you say there?
So those are
Their resolution, they admit it's not even fine enough to do a good job. I think the website said the eddies look too perfect.
Well, what did they say? What did they use? I mean, what did they use to get this?
I would have to check. It's probably, it's only over 10 kilometers. Not 1. So yeah, the southern ocean is actually, as I will show, where these eddy effects are the most important in setting the mean state.
Does this model equate enough?
This is actually a model that is, it's kind of like an ocean weak analysis model. It's fed with any observations available.
So are they
Well, you
mostly
can watch it yourself. Just go to their website.
Shear flows a bit behind into depth and probably, yeah.
Does global, the assimilation office people down there, do they have a,
I think
do they do ocean?
it's the Echo GCM.
So it's a different, right?
The Echo GCM gives some results too.
Yeah,
The
it's
echo
a-
is not that much.
They also use, they use the GFDM ocean monitor there as well.
So they, nothing crazy like that.
Okay, so just a quick explanation of what sets the scale of the eddies. So when you look at the dynamics of so-called geostrophic adjustment, which is a process by which motions come into geostrophic balance. Geostrophic balance is a flow regime where the Coriolis force balances the pressure gradient force exactly. When you ocean is not sloshing around and destroying coastlines all the time. So the importance of the baroclinic, they don't have any net horizontal mass transfer. So if you calculate the speed of the first baroclinic mode, you can solve an eigenvalue problem. And the first baroclinic mode is the one which only has one change of sign of the wave structure. Those speeds are only on the order of a few meters per second, and they depend on the stratification of the ocean and the depth of the ocean. So when you calculate those and then divide by Coriolis parameter or use the equatorial definition of the Rossby radius in the low latitudes, you get a map like this. And the length scales are indeed only a few tens of kilometers in the extratropics. In the tropics, the theory for mesoscale eddies, as Vittorio will tell you, is not as well developed, and so we'll talk about that. It's mainly in the so just to demonstrate that if you have a model with no representation of mesoscale eddies, you're not going to get eddies. I will show an animation of a 1 degree ocean model run with no representation of mesoscale eddies. And you do get things which kind of look like eddies, but the scales are rather larger. And in particular in the southern ocean, so this is showing the potential temperature anomaly function of time. And the only places where you get anything that looks like an eddy are, the Lewis retroflexion and a bit in the western boundary currents. Overall, it's really not as interesting as the movie that you just watched. If you actually run a couple GCM with very weak parameterized mesoscale eddy fluxes in them, the mean state can actually evolve to a very unrealistic situation. So this top plot is showing the depth of the mixed layer around Antarctica during the southern winter, and the mixing is going all the way to the bottom. Whereas if you have eddies of an appropriate strength, this feature disappears.
These eddies, so is it just down gradient transfer, or is there something tricky like up gradient transfer?
It's tricky.
Okay.
So actually, the eddies are doing two things. Maybe you remember the terminology from Vittorio's talk. They're mixing and they're stirring. And so it's this kind of stirring effect, which is most important for what I just showed you. So if you run a model with eddies, parameterized eddies of an appropriate strength, and you diagnose what the zonal mean overturning circulation is, tracer would do if you put it in one grid box in the model, run it for a year, and include this tracer spreading. So on the left is what you get, including this ISO pick mixing, and on the right is what you get with no mixing at all. And a quick animation of so I put some tracer in one grid box here, and I did 400 and something meters. And then I transport it for 1 year with no mixing at all. So it almost circumnavigates Antarctica 3/4. So this movie corresponds to what was in the right hand figure here. So the tracer doesn't spread nearly as much vertically or horizontally. I would think that perhaps the chaotic advection, where the structure of with chaotic advection, the structure of the currents could disperse the tracer. But in fact, most of the dispersion is via the parameterized mixing. And so if you look at what the slopes of the density surfaces are in this region, they're pretty close to how the tracer is spread. This is I should have pointed it out before. I was showing a latitude interval of 50 to 60 south and 0 to 1,000 meters depth. The nominal diffusivity used for that isogeal mixing is close to 1,000, and we calculate a nominal length scale associated with that. After 1 year of fusion, it's on the order of 2 degrees. So back to the temperature now. In the aggregates, mesoscale-eddies act to transport heat out of the deep ocean. They exist because the eddy instabilities reduce the potential energy of the ocean. And the reduction of potential energy implies that the denser water is sinking and it's therefore colder. So if you do runs where with constant diffusivity, and you just increase it from 650 up to over 1,000 meters squared per second, and then plots the area average ocean temperature as a function of depth, you see that the deep ocean actually cools considerably over a time scale of only 300 years, which is a lot less than that 1,000 number that we saw in a previous plot. So we have a lot of work to do in figuring out the right form of this mesoscale diffusivity. Constant value is obviously not appropriate. We're just doing this for pedagogical purposes. If you have some vertical structure such that the eddy vigor decreases with depth, the picture looks a bit different. The warming is much diminished. Depth, so the cooling is much diminished. This is a high-end Torrio et al. Formulation of the diffusivity. And in the deep ocean, it's doing something similar to this simple exponential decay. Why is it that eddies are acting to, in the net, cool the deep ocean? So I just explained it qualitatively, but if you look at the equations being applied to parameterize the eddy heat fluxes, you get expressions like this for the flux. This is what you get if density were only a function of temperature, but it illustrates the point. If the temperature, the stratification is everywhere positive, then this is everywhere positive. It's upward. This is the plot of the heat flux as a function of the
if you're doing down gradient transfer, but this looks all like down gradient transfer.
Well, this is up. This is up. So these positive.
So this isn't eddy diffusivity. That's just gradient transfer. You go down a gradient.
Well, like so.
Up is very it's
So
very special.
It's actually diffusing the thickness of isopycnal layers.
But it is a downgrade.
It is down gradient. I mean, you spark
It's
that
down-
diffusivity. It
Yeah,
sounds
so
like.
Yeah.
But the diffusivity also, the units of stream function are the same as those of the diffusivity. So we have this mixing tensor, which is a combination of down gradient and an advective part. The advective velocities being defined via this stream function. I didn't want to worry about mathematical.
No, but the short answer is not short. The horizontal flux is downgraded, but that's not the only thing that mesoscale does. The other part is not downgraded. The other part is affected.
Well, the horizontal part is purely downgrading if you assume that
Yeah.
the isopycnal mixing, if the diffusivity for the isopycnal mixing is exactly equal to the diffusivity associated with thickness diffusion.
Oh, yeah.
It's kind of a gnarly.
Okay, you don't want to know that.
Max, is this real physics, or are you trying to make up for your lack of resolved eddies by adding diffusion?
Well, qualitative statements like eddies reduce potential energy are pretty well supported, I think.
Yeah, but I mean, that's not fundamental
The way in which
physics.
they reduce potential energy is rather unconstrained, and so I've been trying some other ways of doing it, but I won't be talking about those.
It's certainly parameterizing motions you don't resolve. That's the trick.
So that's what we're doing here.
Yeah.
Yeah.
But it can still be considered real physics if you're,
Yeah.
you have to get the ensemble of what's going on. Right?
Well, there is no imaginary physics, there's only real. So this is a parameterization of something that we cannot resolve. So it's,
Yeah,
we're
so
stuck with
we
it.
need to-
Yeah.
so,
No, I think you shouldn't jump on whether what the term real means.
Okay.
It's not like F equals MA. It's there's F equal MA that we can't don't understand, and so we're adding other parameterizations.
Now the question is it's a standard question when you have this huge amount of scale in the problem. You can resolve only a certain amount of scale, and not all of them. And the one that you don't resolve, whether it's the ocean, the atmosphere, or laboratory turbulence, you have to parameterize, model them, or whatever term it is. And of course, it become the better physics you put in, the more real is your parameterization. And so the name of the game here is to try to put as much physics in it and as much as realistic as it is. And then there is a step that Max does not mention, that before you put them in an eddy non-resolving code as this one, many people check this parameterization against any resolving simulation. Okay, and then when you feel that that is more or less satisfied, then you have some reason to believe the Euro parameterization is more or less realistic in that sense as is the realistic.
we should distinguish between the parameterizations of eddy kinetic energy and the assumed form of what the eddies are doing.
Yeah, but I think his question was more general. Yeah, sure.
So the former is easier to check than the latter. So consistent with previous remarks, larger mesoscale diffusivity, which is re-stratifying the ocean, suppresses the so-called North Atlantic overturning, which is defined as the amount of water descending north, as defined here, descending north of a certain latitude and through a certain depth level. So you get numbers on the order of 15 to 20 spare drops. For reference, the flow of the Amazon River is 0.2 spare drops. Something like that.
What did you plot in here? Oh, the overton.
Yes. So
this is
yes. So with large diffusivities, the overturning is less, and with weaker diffusivities. And when you look
So wouldn't you call them positive feedbacks? Positive feedbacks.
I didn't.
No, I'm saying I would call them positive feedbacks rather than negative, because then they amplify the effect.
Yes. It's, they can either be positive or just not negative. That's a confirming statement.
This is not the United Nations. Just say, call it with his name.
I'm completely confused.
So
That is
the freshwater budget of the Arctic and the North Atlantic is very, very important for the heat transport into the North Atlantic. And as Rainer said, some of the aspects of the problem one would describe as positive feedbacks. So I, in desperation, decided at one point to look at the transport through the Bering Strait. There's a relatively modest transport of order of 1 square drift of water from the Pacific to the Arctic, which then has to go to the North Atlantic. And the width of the Bering Strait in the runs that had been initially configured was a bit too large. So I decided I would try to narrow it, and in fact, it made quite a big difference to the North Atlantic overturning. So these squares are representing the resolution of the ocean model in this region. So it's only 1 or 2 grid points. So when you have to decide between 3 grid points versus 2 versus 1, you know that there's a lot of tuning involved, and we would just like to have finer resolution to not have to worry about that stuff.
Can you describe this positive feedback and salinity?
Yeah, well, so if the North Atlantic overturning weakens, then the transport of salty water from the subtropical North Atlantic will also diminish. Meanwhile, the atmosphere is perfectly happy to keep raining on the North Atlantic, raining out water that get transported from lower latitudes. And so the water can get fresher and fresher, and there's no way out.
As it gets fresher, that reduces the transport?
I mean, it doesn't go to 0. There's
Salinity. So, in this figure, Max, this is an ocean-only run? How's
no, these are coupled runs. In the standalone runs, standalone runs are good for some purposes, but they suffer from the problem that global observations of precipitation are somewhat unconstrained, so we have to resort to relaxing surface salinity to observe values.
So for, even in the coupled run, the volume or the impact on North Atlantic salinity from the Bering Strait flow, isn't that the same order as the impact on salinity in all the Arctic rivers? Like, how realistic are those?
It's a very good question, but it's not as easy to adjust than adjust the Bering Strait. So I may have been trying to compensate for the error in the atmospheric model, but in any case, the original width was too much. Whether I narrowed it too much falls in the matter in the realm of tuning. So there's a similar issue regarding the North Atlantic overturning. When you look at the bathymetry around Iceland and Greenland, the white color is everything deeper than 600 meters. These sills, they're rather strong flows of cold dense water out of the Jin Sea region into the North Atlantic, and they descend along the slopes there. And GCM can't do this with the assumed was not so very different than the frozen air 5 version. The version used for runs submitted to CM5 database. But in fact, a couple of changes in the cloud scheme resulted in a large change in interbasin vapor transports in the atmosphere, and which were acting to freshen the North Atlantic, which was bad for the North Atlantic overturning. Although the cloud changes, would not have been put in if they had no positive impacts, obviously. So they actually improved the Amazon discharge quite a bit. So it may have been that the model was getting reasonable overturnings, for the wrong reasons or slightly wrong reasons before, and this is something that we'll definitely need to figure out when we start doing more runs using the latest cloud scheme. And
Do you mean the processes?
no,
Water vapor transport or what?
the Indian, somehow the vapor transport over Africa, because the Indian got a lot saltier.
Max, do you have a reason to believe that those changes are unrealistic for other reasons? I mean, like observational reasons? Because it looks like there's a lot of things affecting overturning. I'm just wondering,
The cloud changes,
No, not just, for this vapor
I
transport,
don't
for
want to,
instance.
we don't have time to go into all those cloud changes, but we can discuss it more offline.
I was just wondering about observational constraints on, each of these elements, like that flow through the isthmus, and, all this.
Yeah, there's a lot of data out there that one can look at, try to guide the model development. Okay, another salinity story is the following. Running the standard Air 5 atmosphere, not the new one, after 100 years, you would find that in the Indian Ocean, the temperature at a pretty deep level would warm by several degrees. And this level is far below the influence of small-scale mixing. And the large-scale circulation was not bringing down warm water from above. So I was scratching my head trying to figure out how it is that the model would warm up so much. And when I looked at some other model runs, and like this one, which is using a cube sphere model, I found that the warming was much reduced. This is what you get using the standard ocean configuration. With not exactly the same diffusivities, but qualitatively it's kind of similar to, at least in this area, similar to this run. And you look at the salt, you see qualitatively very similar shapes. So salt and temperature have opposing effects on density. So you can create warmer, saltier water, which has exactly the same density as the initial condition in the model. But of course, so from the dynamics point of view, a lot of this anomaly is kind of invisible. But unfortunately, that warm water is going to eventually go somewhere else in the ocean. So we don't want to allow the temperature to drift so much. So I eventually found that there was this very vigorous vertical mixing happening along the coast of Asia, particularly in winter. So in this reference run, the hydrology, the freshwater budget of the Indian Ocean was such that the surface ocean was getting too salty here. So the atmosphere was transporting too much vapor from here over to the Pacific, and
The excess water from the Caspian Sea goes there too.
And there was also a problem since you mentioned that, there was also a problem in the river routing scheme, which was withholding a lot of water in a very deep lake in Asia, which was not the actually in the runs they were tending to get saltier, that volatility goes in the wrong direction.
Are there any model in the world that are free of such problem?
This particular
This model.
well, I mean, a lot depends on how good the atmospheric vapor transport
This
is.
symptom, are there any model can go without such problem? Other group?
It depends on their atmosphere model. So just to explain what was happening, and this isn't clear. So this salty warm water was being mixed downward along the coast, and then it was being laterally dispersed by the mesoscale eddies along a surface of fairly constant density, actually. Okay, quick remarks about the long time scale effects of the ocean. So to get this right, we need the right amount of diagonal mixing. We need it to be happening in the right places, and we need the large scale transport pathways to be correct. To bring, for example, warmer surface water that has been warmed in response to radiative forcing, to bring that the right manner into the deep ocean. If there were no deep ocean, then the ocean obviously could not store much heat, and the response of global mean temperature to radiative forcing would be much faster. So just one example of the effects of the combined effects of mesoscale mixing and small scale mixing. The top slide is showing the whirling pattern in a run which had this excessive vertical mixing around Antarctica. The bottom slide has that mixing in check. This is a 100-year temperature difference in some transient seaman pipe runs that we've done. And you see that the warming spreads very quickly to the Southern Ocean. There's vigorous mixing. And so the net ocean heat uptake was actually not drastically different in this one, but a couple of minutes on the top. Now to Eric, how much more time is there? 0? So over. This is the last topic, fortunately. So the ocean as a generator of variability. So ENSO is the most famous example of that. ENSO ENSO is a coupled phenomenon, but its existence requires this rather pronounced slope of the isotherms in the Pacific, which is there because of upwelling. There's also upwelling in the Atlantic, but for various reasons, the slope of these isotherms is not as pronounced, and there's not such a large. The Atlantic doesn't have it, so. These two plots are showing the effect of switching the advection scheme. The model does not really have a large number of layers to resolve this temperature gradient here, and the curvature of the temperature profile in particular. And also the equatorial undercurrent is one of the strongest currents in the world. The speeds on the order of 50 centimeters per second in places. So it's bringing warm water eastward, but it's supposed to be rising at the same time. And so you can imagine that the details of the advection scheme would matter for the temperature structure. This is showing the temperature drift after 100 years, and the bottom plot is the better advection scheme, and it has a reduced warming. And there's no time to discuss this. Just to show the effect on the ENSO variability, this is the observed interannual standard deviation of SSTs from the Hadley Center data set. And so this is ENSO here. And this is what you get with get using the better advection scheme, and it's for the magnitude on the order of the observed one. Fortunately, there are biases in the atmospheric model and in the ocean model, which over time reduce the amplitude of the signal. But this is some small measure of progress, since historically ocean models have a hard time, or at least this ocean model has had a hard time getting a large ENSO magnitude. I'll leave it there.
So the two advection schemes there, QUS and RED. What was the other advection scheme?
It's a kind of a hybrid of the linear upstream scheme and center differencing. I think it's not only the vertical direction which matters in this case.
Sounds like really cheap advection.
No, the linear upstream scheme doesn't mean that it's first order accurate.
You mentioned the Atlantic region, fresh water become fresh and fresher. My question is, are there any group correct?
Any what?
Any group?
Well, I mean, this model has had a stable and
No, I don't mean GISS. I mean German and Anchor.
well, many models have problems maintaining a
Is
stable.
it a common problem or it is just?
It's a common problem because, as someone said, there are positive feedbacks, and so you could have some reasonably good atmospheric model, but if something slightly tips the balance towards a freshening relative to what it should be, these positive feedbacks can
Did you look at the drifts with the QUS, as you did, for example, with some of the mesoscale parameterizations? Did you look at?
It's mainly, the effect is largest in the tropics, as I said a few times, and in the standalone runs, the effect is not as dramatic. But it is noticeable, but the feedbacks, in this case, somehow, for reasons I don't fully understand, keep a larger ENSO amplitude of QUS. Yeah, the advection scheme has been blamed for many problems in the model over the last 3 years, some of which turned out not to be, some of that turned out not to be the case. But this more expensive advection scheme is what we will use going forward, since the default one does a reasonably good job for things like temperature and salinity, which have usually a fairly smooth structure at this resolution. But for arbitrary tracers, that may not be the case. So let's use QUS for all transported quantities. Think about it.
What's the price?
Actually, just for completeness sake,
Nothing can be complete in an hour.
well, not completely your thought. I mean, even if we solve the problem, there is still a physical process that is not resolved by anybody, and that is, well, not by anybody, almost all, and that is gravity current. And gravity current, like the one that has been driven not by diagonal mixing, it's gravity current, like the one in Gibraltar just falling down, and that like the one in the Denmark Strait, etc. Because a huge amount of water is being oversailed. So I don't think that's a question of resolution of law. It's a question of there's a big chunk of physics that's missing.
What physics is missing? It's not negative buoyancy to dragging it down?
No, well, yeah, but it's not a diffusion process at all. So you cannot represent it with the standard method of dealing with the problem, more or less of some diffusion.
So
this is really gravity.
It's sub-grid scale is the problem. It's sub-grid scale.
Well,
and not the
physics
destruction.
don't resolve it, everything is sub-grade in a
Right.
sense, but the physical, this is very different. It is this current that simply fall down and go along the bottom and change the vertical structure of the water, because they go so fast that they bring down all the salinity of the Mediterranean, for example, it's very salty all the way to the bottom in almost no time, and then destroy. And that happening presumably in many other places, but the ones that are more conspicuous are Gibraltar and Demonstrate, that's right, which I went to the literature very thoroughly, and there's very few code that can resolve it. They have no, it's not going to resolve, sorry, they have a proper model, treatment, that's right. Let's use the word treatment.
Wait, if there's a proper treatment, why don't you put it in your model?
Because I don't have it. I
Some
wish I had the
equations,
model
put the
for
equations
treatment.
in.
No, I wish I had the model for gravity current. Then I will put it in. But you have to build up the model first.
Yeah.
And that is a highly non-trivial. Because you see, this water comes down and train water into which is falling.
Mhm.
But the two type of water is very different. One may be very salty, the other one not. And so the salty one keeps training the other one until it gets practically the same density as the other. So it's an entrainment problem, which is very different than any of these kind of things. And so we better with the Gaussian than it. There's a lot of lab data because they can really simulate it very nicely. But how to parameterize it or model it in OGCM, I think we're still very far away from it. And that's something it's a considerable drawback into this, especially in those regions that you were mentioning.
Why is it so contradictory?
Well,
Gravity, buoyancy, density.
yeah, sure, it's always gravity.
I've actually.
I'll tell you, I answer this question. I'll tell you what, you have this plume coming in, okay? I call it the plume.
Yeah.
Now, the process between the plume and the outside water occurs at the surface, when they are in touch. And that is the reverse of what happened with the volcano, for example. They spew out tons of dust, for example, and then it's being entrained by the atmosphere, which is a different depth. And at one point the two become the same, and the entrainment is over. Now the only model there is the one for the atmosphere, precisely, that worked out as usual by G.I. Taylor back in the 50s. And I'm becoming too long my answer, but the transformation or transport of that process to the ocean has been done, but it requires such a huge program that you cannot attach it to another code like this. So you need a much simpler representation of that phenomenon that it has been done, because otherwise you just cannot afford it. And that simpler representation
It's computationally expensive.
if you want to do it the way it has been
Right,
done,
right.
yeah, it could be this very expensive, so it's prohibitive actually. So you have to find this, because it's not only a question of doing the physics more right, it's also the question of doing something that's manageable, that can be taken up in this code, because otherwise, if you give them a perfect model that takes all the computer time all by itself, it's useless. So
I've been trying some manageable things, and I was thinking